everyone to be here. So, as already Claudio mentioned, I will talk about a little bit of the KLT. I'll go a little bit into detail. Sorry, the talk will be kind of technical, a little bit mathematical. I'll try to be slow and clear as much as I can. So let's just start with a little bit of history. So the idea to use the KLT as noise filter in order to recover signal of interest, from now we will call it as simple SOI, was proposed during the 80s by Birod and then further explored by Marconi during the 90s in the context of SETI. Recently, the KLT has triggered also an interest in general in the astronomical community, since it's already explored, is already studied for cosmic microwave background power spectrum estimation, filter array 21 centimeter computation, and so on and so forth. So, okay, let's just introduce what is a stochastic process, because I want to try to be clear as much as I can. So, a stochastic process is more complex mathematical structure. It's more complex than a random variable, than a simple function. It's something in between in a certain sense, in the sense that in order to be characterized, you need a scalar parameter, which might be the time or whatever you prefer, but also can be characterized in a probability space, because basically it's just a random variable which depends on these scalar parameters. For instance, in this picture, I'm showing several realizations, what are called mathematical realization of a stochastic process. Also, Claudio showed something similar with a Brownian motion, in the sense that of this kind of random function, you might have different outcomes. Stochastic processes are quite common in science in general, representing biology, climatology, economy, astronomy as well. In fact, the signals received from an antenna basically are stochastic processes. Okay, let's start with the KLT. Okay, let's try to be general and consider a complex valued stochastic process defined in a time interval. On the left, you can see the standard Fourier expansion of this stochastic process, while on the right, you can see the KLT expansion of that. In both cases, the coefficient will be random variables, while the basis function will be deterministic functions. But the main difference is with Fourier, basically you are forcing the basis in the sense that you are considering always complex exponentials, while with the KLT, you have the freedom to use a different set of basic functions. There is a way to compute these basic functions. Here I'm showing just the main equations for the KLT, and basically this is the way we compute this basic function. It is just a eigenvalues problem, if I so know something about quantum physics and whatever. So basically these basis functions are eigenfunctions of this operator, which is I'll call autocovariance operator of the stochastic process. And later I will discuss a little bit more about how to compute this autocovariance operator, which is extremely important. Mu is just the mean of the stochastic process, but it's not so important in this case. I mean, R is the main important thing to remember. How does it work, the KLT as noise filter? This is a conjecture, but it seems working, apparently, surprisingly. The idea is, okay, you solve the KLT equation, you find your basic functions, the eigenvalues of your problem, then you sort your eigenvalues in a decreasing order, and you just do what is called commonly plot an eigenspectrum, as the two figures on the right. And turns out that if there is a signal buried in the noise, the eigenspectrum shows very few dominant eigenvalues, while when there is no signals, you tend to have a continuous eigenspectrum which doesn't show any kind of particular feature. So the conjecture is, okay, suppose we have a stochastic process which consists by the sum of two terms, our SOI and the noise. In theory, if we perform the KLT and we stopped the expansion at the order of the dominant eigenvalues, we can recover the SOI. Turns out that most of the time it's extremely hard to find the optimal number of coefficients, since the eigenspectrum sometimes doesn't show any particular features. I mean, these are basically a common problem in multivariate statistics, because the KLT is basically what is called also in multivariate statistics PCA. And also statisticians have some troubles to understand the optimal number of eigenvalues. Okay, so let's talk about KLT for discrete processes, because now we were in the continuum, but in real applications, stochastic processes are always discrete. You know, when you measure a signal, you are sampling in time, so you have a set of numbers, no? So one first thing we need to do is how to estimate R and mu, as I mentioned before. Here we have a main conceptual problem. Sometimes you might have several realizations, as I mentioned before, of the stochastic process. Other times you have only one realization of the stochastic process. For instance, think about a signal received from a telescope. You point on the direction, you measure a signal, and you will have basically only one realization of the process, no? So we have our initial input for the KLT might be a matrix in general, where you have more realization, no? Or a single vector, basically, when you have only one realization. Okay, let's start with the case of, okay, we are lucky we have more realization of the process, so we have a more complete overview of this. So, as already mentioned, the input will be a matrix, and then, thanks to multivariate statistics, we can estimate R and mu, as I showed here. I mean, the equations here are not so important for now. Then we can perform the KLT and try to reconstruct something. Okay, here I'm showing a linear chirp buried in colored noise, just to be more general as I can. I consider 10,000 realization of this chirp, so basically you have 10,000 chirps buried in the noise, okay? They have the same starting frequency at the same drift rate, but they have a different phase, generated randomly. Okay, let's start first with the eigenspectrum. Here, this is just the legend, are not the eigenvalues of the eigenspectrum. So as you can see, there is one dominant eigenvalue, and then we have this continuum line, no? So I say, okay, nice. Let's try to reconstruct the SOI using one eigenvalue. On the right, I'm plotting the power spectral density of the blue line is the received signal without any kind of KLT, just FFT and then compute the power spectral density. As you can see, you can't see anything. Then on the bottom, you can see the green is just the power spectral density of the SOI clean without any kind of noise. And the red one is the KLT reconstructed. As you can see, the KLT managed to reconstruct quite well the SOI buried in the noise, find rightly the starting frequency, no? Which is the starting point of this plateau, and then also reconstruct quite well the drift rate of the chirp, which is the broadness of the spectrum. The SNR was quite low in this case, like minus 20 dB, which is extremely low. Here, when I consider more complicated scenario, like I simulated a synthetic FRB with thanks to an external collaborator in Australia, and here, just because it was much more cool, I just plotted the waterfall plot of the synthetic FRB. On the left, you can see the received signal, the spectrogram of the received signal. You can see a little bit of the synthetic FRB, but it's quite blurry noise. On the right, while you can see the Kelty reconstructed spectrogram, and here it's pretty clear to see the FRB and the typical dispersion effect. In this case, obviously, the SNR was a little bit higher, minus 10 dB, because the problem with the multipolarization Kelty, if you try to, when you start to consider more complicated signal, you have to consider way more realization, and then you have a huge computation problem. And since my project was a kind of internship project, I need to use my personal laptop, so I had some issue to handle with huge amount of data. But anyway, even if you consider more elaborated signal, this multipolarization Kelty seems manage to filter out noise. One huge issue, obviously, is the extremely high number of realization, because the problem is, okay, nice, we are reconstructing our SOI, but I'm considering 10,000 realization of the signal. And what does it mean, 10,000 realization of the signal in astronomy? One potential applicability might be consider array of telescopes, and then every complex voltage recorded by a single array would be now rare in the realization of the process. But obviously, it's a technology, no trivial technological problem, since you need to have 10,000, 100,000 telescopes. Okay, so let's try to handle with one single realization of the process. So we are doomed, we have only one realization. What am I supposed to do? Usually, when only one realization is available, the standard approach is to assume mathematically that the process is White-Sands stationary, in the sense that the mean is constant, and the autocorrelation depends only on the time lag. In that case, one can prove that we can estimate the mean and the autocorrelation in the following way. So basically, we build the autocorrelation vector, and then we put the elements of the autocorrelation vector in a Toeplitz matrix. So the Toeplitz matrix will be our covariance matrix. And then we perform the Kelty, as is shown in this equation. This method is extremely successful for sine waves, as proved by McConnell, but for more complicated signals tends to be kind of limited, in the sense that the Toeplitz approach tends to reconstruct only with base of sine waves, so it's not that different from Fourier, basically. So when I try to mimic the idea of multiple realization, I thought a new method, which the main idea is, okay, suppose my initial input, so the signal burden has a periodicity, so it's a periodic signal. Then I can divide my initial vector into k subvectors of length w, okay? Then I can just reshuffle my input and basically a matrix as input. Then I can compute my mean, my covariance, as I shown here. And then I can perform my Kelty. Then the reconstructed initial vector will be just the rearrangement of the Kelty reconstructed subvectors. Obviously, there is a constraint in the sense that you need to consider periodic signals. Obviously, this method is not suitable for single bars like an FRB. No, you have noise, 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 signal, noise, noise, noise. So definitely not suitable. But for instance, in a pulsar case, if you know the period, you can just divide your signal in several chunks. As Andrea already mentioned, the KLT has a problem, a huge computational problem. Here I'm showing time analysis, a comparison between the tapered KLT and my covariance KLT. As you can see, the covariance KLT is way more faster, since the idea is when you divide in several subvectors, you have basically smaller covariance matrices, because the main issue of the KLT is just compute eigenvalues and the eigenvectors. It seems strange, but for a computer it's extremely complicated to compute an eigenbasis, and it needs a lot of time. Here, for instance, I'm showing a more complicated signal. Is a binary phase shift keying, which is basically a sine wave which is phase is discretely modulated in order to have your bits and send your information. It's typically used in satellites for the telemetry signals. As you can see, the standard tapered KLT doesn't show any particular feature, while the covariance KLT shows one dominant eigenvalues. And then, in fact, you can see from the reconstructed power spectral densities that the tapered KLT is trying to reconstruct the initial signal with a base of sine waves, while the covariance KLT correctly reconstructs the spectrum. As a real data application, I did a covariance KLT for the Voyager 1 telemetry signal. The Voyager 1 telemetry signal consists basically in biphase modulation, where the center carrier is 8,000 megahertz, and which contains also the subcarriers. They are modulated, and then they send the information basically. Okay, so this is the CKLT performed on the Voyager 1 telemetry signal, which was recorded by the Breakthrough Listen group at GBT. As you can see, the eigenspectrum is a little bit complicated in the sense that you have one very dominant eigenvalues, and then you have a little bit of cluster of subdominant eigenvalues, and then you start to have the not dominant eigenvalues. Then say, okay, let's try to reconstruct with the KLT the Voyager 1 signal, and in this case, the first one I consider only one eigenvalue. As you can see, basically, the KLT reconstructs only the main carrier, basically. Then I consider, in order to see all the free carriers, I need at least 3 eigenvalues, as in this image. In order to have the most clean signal, I needed to consider 9 eigenvalues, which are the very first dominant and this cluster here. As you can see, we have a huge gain in power. I mean, here we have if this is the received signal is 6 dB. Basically, the power here is like 30 dB. So we have a gain of 25 dB. Obviously, this case shows that it's very complicated KLT science, because I mean the eigenspectrum it needs to be understood well, and might be complicated for blind searches, since you need a scientist which look the eigenspectrum, try in different ways in order to have a control of it, no? So in general, I mean, when in the case you have multiple realization, the KLT is extremely successful to reconstruct SOI Burette noise, while obviously showing promising results is definitely not suitable for single dish telescopes. And standard KLTs with single realization shows in general good performance for sine waves. The new covariance KLT show a more broad applicability, but it has limits as well, since you need to consider periodic signals. So in general, just to conclude, the KLT might be an interesting object, I would say very powerful for interstellar telecommunication, while for astrophysical signals might be extremely problematic, since most of the time you don't know anything about the signal you are looking for. While for engineering science, I mean, you know the specs of your satellite, and you know what are you looking for, so you have a more control of it, no? Thanks.
That are intended to explain better the real novelty of all this. First of all, the name. When I start, thank you, sorry, just some explanation to make the ideas clear. So, the KLT was the subject for my PhD thesis at the University of London King's College in the Department of Mathematics before 1980, right? But of course, at that time, I was just a mathematician doing all the work and so on. Incidentally, in that book that is shown over there are 10 chapters devoted to the KLT. Okay. Now, first of all, the name. KLT I used because at that time there was no internet. So, K stands for Karhunen, who was a Finnish, actually, that is a mathematician of finances, who wrote his PhD thesis at Helsinki in German. And you say, why in German? Because during the Second World War, Finland had been siding with Nazi Germany. So it was customary for them to publish scientific works in German. And this was not translated into English until 10 years afterwards, first. Second, the L, after the K, comes from Michel Loeb, a French researcher that rediscovered the same idea about the same time, it is after the Second World War, and published that in French. I speak French, so the théorie des processus stochastiques de second ordre, theory of stochastic processes of the second order. Good. Loeb did it better, because after not being understood in France, he emigrated to Berkeley, and he set up such a good school of probability that even today, after he passed away a long time ago, there is the Loeb Prize for young mathematicians working in probability statistics. Okay? Enough? Not at all. Before these two guys, a third guy that actually was the first guy was an Indian mathematician, Kozam. Now, India at that time, you have to understand, was a British colony. So he published that in English, but since it was the Second World War and nobody was caring about whatever was going to publish in India about mathematics, it was unnoticed. So this is the first comment. The second comment is about the application. These two very good pupils, and there is another pupil, but that is about another story. Just look at my words, and I pursue the research. The point is, however, that the KLT is not only good for filtering signal, that is recovering very weak signals out of the background noise. It is also good for compression of data. That is, when you have a space mission and you send it out, for instance, the Gaia space mission around the moon, and I know what I'm talking about, this is true example, because Gaia is an ESA mission, and when I was working on space mission, I was involved with that. So you have this spaceship going to the moon distance. Then it has to download a number of data, right? But before doing so, you have to compress the data, because otherwise it will take centuries to download the data. The KLT is exactly the best tool to compress the data, also. So it's a double use thing. Final point. those who love quantum physics, and here there is someone who, she is not here, Maria, she loves quantum physics. Good. Now, let me say the same story in the language of quantum physics. The KLT is the mathematical apparatus of quantum physics translated into the language of signal processing. So, what here is called the integral equation of the Caruana-Loeb transform, which is what I solved by hand when I was doing my PhD in London for a particular case, that is essentially the eigenvalue equation for the operator called the autocorrelation of the stochastic process. So, in conclusion, when you have the equations on your hand, then you have the real truth. If you don't have the equation, you are just talking. But if you understand the equation, you understand that essentially it's the same thing, discovered by different people, with different words, with different purposes, but the equations are just the same. And this is the good point of mathematics.